Good afternoon to you viewers and subscribers. Welcome back to my channel and welcome back to another video. In today's video, I'm going to talk to you about cantilever slab. So before I get into the presentation, I'm going to give you a short synopsis of what a cantilever slab is for the benefit of those who are watching the video and do not know what a cantilever slab is. A cantilever slab or a cantilever beam is where you have one end fixed, right? And the opposite end is free. Or in layman's term, is a portion of a slab or a beam that is projected away from the building without support, right? So usually in designing a cantilever slab, the first thing the engineer needs to obtain is the amount of deflection that is in the slab, right? The amount of deflection due to the load that cantilever slab is going to be subjected to. So if that deflection surpasses a certain amount stipulated by the ACI code, then the introduction of a slab or a column or a beam that is needed to be designed to withstand the load and to limit the deflection of the slab itself and to prevent the slab from failure that can cause damage to property and loss of life. Because I do not want someone to be standing on their cantilever balcony or sitting, relaxing, or whatever the case might be, and that slab is not designed properly to carry the weight, and the slab fails and it causes severe damage or even loss of life. So to do this video, I just want to give you viewers and subscribers an appreciation of what goes into the design of a cantilever slab so that it can be safe enough for the occupants to utilize the slab without the slab fail. Especially if that slab is projecting a significant amount of length away from the building. If the slab is projecting like 2 to 3 feet, usually I do not do a deflection calculation, but if it's going to be projected beyond 3 feet or more, then it is quite necessary, vitally important for us as engineers to do a deflection calculation to determine how much that slab is going to deflect under the impended load or the load that that slab is going to be subjected to. So I want you to watch the video until the end, subscribe, like, and share. All right? Stay tuned for the video. So this is the cantilever that I'm going to be talking to you about. I'm going to show you how to calculate the amount of deflection that is in this cantilever based on the amount of loads that this cantilever is going to carry. Now, this portion of the slab is the floor slab, and the cantilever balcony, which is a cantilever slab, is attached to the building and it is projected 6 feet away from the building. So the dimension of this cantilever balcony is of a thickness of 6 inches by 6 feet projection by 12 feet in length. So in engineering design, when we're designing a member, we usually design for 1 foot length. So if this slab is 12 feet in length, we only design for a 1 foot strip. All right. So this diagram below here is the cantilevered balcony. So if you'll notice, it is projected away from the building 6 feet. All right. And remember what I've said in the intro, a cantilever is a member that has one end fixed. So this end here is the fixed end, and the opposite end is free. So this end here is the free end, and this end here is the fixed end. And if you observe, I have taken a 1 foot strip. I do not need to design the entire length of the beam. So what I'm going to do is to design 1 foot, and then I can duplicate that 1 foot design throughout the 12 feet. All right. So there's a couple of notes here that I want to read to you before I get into the calculation. So it says, please note, for a residential building, we use a live load of 40 pounds per square feet or 2 kilonewtons per meter square. All right. So for dead load of the cantilever slab, the dead load of the cantilever slab is going to equal to the self weight of the slab. All right. And we're going to design this according to ACI code table 9.5b section 9.5.3.1. So we're going to use the ACI code to guide us through this deflection calculation. I'm not going to go into the codes because if I do that, the video is going to take a long time. So I'm just going to introduce the part of the code that I refer to get the necessary information in terms of how to carry out the deflection calculation. Okay? So the code, table 9.5b, section 9.5.3.1, it says that the maximum permissible deflection for floors not supporting or attached to a non-structural members that are likely to be damaged by large deflection is L over 360. That means the length of the cantilever slab, the amount of projection divided by 360. So at no given time, your deflection should exceed this value of length divided by 360. All right. Now, to go into the calculation, so using a 1 foot strip, which is 6 inches in thickness, 6 feet in length, and 1 foot in length. So it is 6 inches in thickness, 6 feet in terms of the length of projection away from the building, and in a 1 foot strip. So we only design for 1 foot. So step 1, we are going to convert this 40 pounds per square feet to pounds per foot, because we want to convert this 40 pounds per square feet into a uniform distributed load of pounds per foot for our live load. All right. So since we are using a 1 foot strip, we simply multiply this 40 pounds per square feet by 1 foot, and we get 40 pounds per foot. Or a longer way, but a more secure way, how to derive that 40 pounds per foot. So I'm going to take you through the longer calculation. So the weight of the slab, right, which is the dead load, is going to be 6 feet times 12 feet times 40 pounds per square feet, which is going to equal to 2,880 pounds. Right? So the dead load of this slab, the entire 12 feet length by 6 feet projection by 6 inches thick, is 2,880 pounds. That's for the entire weight of the slab, the full 12 feet length. But we do not want a full 12 feet length. Remember now, we are only working with a 1 foot length. All right. So since we are working with a 1 foot length, the area of that 1 foot length is going to be that 6 feet, which is this 6 feet here, right, times 1 foot, right, which is going to equal to 6 feet, right, times 40 feet, which is going to equal to 240 pounds. All right, so this six feet, the reason why I multiply this 6 feet by the 1 foot length is to give us 6 square feet. And this 6 square feet meaning that every square feet along that 1 foot strip, it is going to have to multiply by 40 pounds per square feet, because for every square feet the live load is going to be 40 pounds per square feet. So if you times this 6 square feet by this 40 pounds per square feet, the result is going to equal to 240 pounds. So this 1 foot strip of the cantilever slab is going to weigh 240 pounds. So that 240 pounds is going to act at the center of the cantilever slab. All right, so because we want to get this 240 pounds, we want to convert it to a uniform distributed load, we have to divide that 240 pounds by 6 feet. So it is going to be 240 pounds divided by 6 feet, which is going to equal to 40 pounds per foot. So you see, if you observe, in this instance, when I multiply the 40 pounds per square feet by 1 foot, the result is 40 pounds, right? And when I take the longer route, it still comes back to the 40 pounds. Now, if I was doing the calculation by myself, I wouldn't go through this second portion here, right? This is just to show to you viewers and subscribers, in the event that you don't know how I just simply multiply this by 1 foot to get the 40 pounds per foot. I take you through a longer route and show you I still get back my 40 pounds per foot. When I do the weight itself of the 1 foot strip divided by 6 feet, I get back my 40 pounds per foot. All right. Now, so that is for the live load. Now the dead load is going to be the dead load of this 1 foot strip. So the dead load of this 1 foot strip is going to equal to 6 feet, which is this 6 feet here, times 1 foot, which is going to be this 1 foot here, times 0.5 foot, which is this 6 inches here, times 150 pounds per cubic feet. So the unit weight of concrete is, the unit weight of reinforced concrete is 150 pounds per cubic feet. If it was unreinforced concrete, it would be 142 pounds per cubic feet. But since we are going to have reinforcing bars in this 1 foot strip, we have to account for the weight of the bar. So the unit weight of the reinforced concrete is going to be 150 pounds per cubic feet. So when you times that out now, you're going to end up with 450 pounds. So that means this 1 foot strip of the cantilever slab weighs 450 pounds. But because we want to get it into a uniform distributed load, I divide it back by 6 feet to get it to 75 pounds per foot. So when you divide 450 pounds by 6 feet, the result is 75 pounds per foot. As again, if I was doing the calculation, I would just simply leave out this 6 feet and multiply this 1 foot by this half of a foot times this 150, and I will get back my 75 pounds per foot. But I'm doing this in the case of if someone is watching the video and want to understand how to do this the right way, the video captures that and someone can follow my calculation easily. I didn't go the advanced way. As I said before, if I was doing the calculation for my own purpose, I would take the shorter route because I already know how to derive it the long way already. Alright? So we have calculated our dead load, which is 75 pounds per foot, and we have calculated our live load, which is 40 pounds per foot. So we're going to use now our LRFD design method, the load resistant factor design method. There are two design methods in concrete design and in steel design. There are ASD. ASD is allowable stress design, and LRFD is load resistant factor design. Now, load resistant factor design is a newer design. Previously, back in the early 40s, 50s, the design method was ASD, allowable stress design, but we are using LRFD now because it is more convenient to the modern world. So we're gonna have LRFD, so we're gonna factor our load. So we're gonna factor our load by 1.2 dead plus 1.6 live. We beef up our load. If the load is 10 or whatever figure, we find 20% of it, and if the after dead load and if the live load, we find 60% of it. So that is why we times our dead load by 1.2 and our live load by 1.6. So when we times 1.2 times 75 pounds per foot plus 1.6 times 40 pounds per foot, the ultimate weight on the slab, uniform distributed load, is going to be 154 pounds per foot. Alright? So we can move into the deflection calculation now. So this is the deflection calculation formula. It is minus WL to the fourth over 8 EI, and the result of that must be less than or equal to 306 to L over 360. Alright? So we have do not focus on the minus. The minus is just telling us that the load is coming down. Okay, so this is just a sign convention. So we have W, which is the weight, we have L, which is the length or span, and we have E, which is the elastic modulus of concrete, and we have I, which is the moment of inertia. Alright, so for normal weight concrete, the elastic modulus shall be permitted to be taken as 57,000, the root of the compressive strength of concrete, and that is governed by ACI code 318 section 8.5 page 111. So I'm using a compressive strength of concrete of 3,000 psi. So when I find 57,000 times the square root of 3,000 psi, the result is 3,122,019 psi, or 3 times 10 to the 6 psi. So we're going to use 3 times 10 to the 6 psi for short. Then our moment of inertia now, which is going to be BD cube over 12, the breadth, times the depth cube over 12. So since we assume a 1 foot length of the slab is going to be of a length 12 inches, which is going to be 1 foot, and it's of a depth of 6 inches. Because the reason why we convert this we use this 1 foot as 12 inches, and we use this 6 inches as 6 inches and not 0.5 feet and not 1 foot. We want our answer to be in inches. So everything has to be in inches. The elastic modulus of concrete is 3 times 10 to the 6 psi, and our moment, which is pounds per square inch, and our moment of inertia is going to work out to be 216 inch to the fourth. So it's going to be 12 inches times 6 inches cubed divided by 12, which is going to be 216 inch to the fourth. Alright? Therefore, having converted the moment of inertia to be 216 inch to the fourth, so we can now utilize the formula to calculate the amount of deflection. All right. So the amount of deflection is going to be 154 pounds per foot times 1/12, because remember I've said to you that everything in the deflection is the result we want. I want the result to come out in inches, so I have to convert my foot to inches. Okay, so that is why I times this 154 pounds per foot times 1/12, right? I simply just divide that by 12. The 6 feet, which is the length, I times it by 12 also, right? 12 inches to carry that 6 feet into inches, and that is going up to the 4th power, right? And it's going to be 8 times E, which is the elastic modulus, right? Which is going to be 3 times 10 to the 6 pounds per square inch, all right? And then I, which is the moment of inertia, which is going to be 216 inch to the 4th. All right. So everything is in inches. So when I work that out now, I'm getting 3.4 times 10 to the 8 divided by 5 times 10 to the 9. And the result is 0.068 inches. All right. But remember I've said, based on the ACI code, the maximum allowable deflection is going to be L over 360. So this is going to be the 6 feet times 12, because remember the projection of the cantilever slab away from the building is 6 feet. So I have to convert that 6 feet to inches and divide by 360. So that gives me a result of 0.2 inches. So therefore, we have 0.068 inches is less than 0.2 inches, which means the deflection is okay. All right, because it is not, the deflection calculation is not surpassing the length divided by 360, which works out to be 0.2 inches. So this is an eye-opener, because oftentimes when I see cantilever project 6 feet, automatically I said to myself that, you know, it looked precarious, it looked like it needs support. But that's what I'm saying, that's what I've said to a lot of people, that we as engineers, we let numbers do the talking. We use formulas, mathematics and science to do the calculation, to advise the clients in terms of what type of support or what type of structure they can build for it to be safe. But having said that, even though it is okay, if you observe, and let me go quickly back to the cantilever here, you notice there are no railings on the cantilever. So if you're going to put like a block wall on the cantilever balcony, right, as railings, then I have to do the deflection of that. But if you're going to put like a lightweight railing on it, then it is going to, to my estimation, it should be safe, because that amount of lightweight is not going to make any significant change. But if you're going to put column on the cantilever balcony, or a low reinforced concrete 6 inches block wall or 4 inches block wall, then I have to do the calculation and see how much the deflection is to determine if it's going to need a cantilever beam for support. Okay? And remember now, engineer, there are 2 criteria which a client should source an engineer to obtain. An engineer deals with safety and economy. So yes, you send a drawing like that to the Parish Council, quickly they would say, oh yes, it wants a cantilever beam, without doing the calculation, because recently I've had an experience with it, right? And that's why I sat down, do the calculation and say, no, sometimes they make it look like, you know, the world is coming to an end when they see a cantilever projection without a beam support. But you have to do the calculation. Next thing I want to point out before I end this video, you have to ensure that you use the required strength of concrete. Because if you just arbitrarily mix up concrete on site, which you can't determine the strength of that concrete, right, you can end up with that cantilever slab failing. And that is why I said I use 3000 psi. So if you're building your dream home and you're doing this cantilever, it is best for you to order the concrete from the concrete mix or the concrete plant to produce you with the strength required, the strength of concrete required in order to obtain the stiffness of the slab itself so it won't fail. Because this 3000 psi here, it is in the calculation, right? It is in the, let me see if I can find it. It is in the calculation, right? Right. The elastic modulus of concrete, meaning the amount of stretch the concrete can stretch, right? So it is 3000 psi. So if you use a concrete strength which is less than 3000 psi, then you're probably going to be in problems or trouble, right? So it is designed with a 3000 psi. You have to ensure you use a 3000 psi concrete. So you have to order it from the concrete plant, tell them that you need a 3000 psi to pour your concrete. Don't just try and mix up any concrete on site and then you pour it and say, oh yes, the engineer said that it doesn't need a cantilever beam for support, right? Because it is safe. No, you have to ensure that you use the required material, right? So this shows that it is not going to need a cantilever slab a cantilever beam for support based on the amount of deflection. But deflection doesn't exceed the 0.2, right? So the next thing you need to do as engineer, as I would have done, is to design the amount of reinforcement in that 1 foot strip of slab. So in the next video, depending on how this video perform, I might design the amount of reinforcement to go into that 1 foot strip, into this 1 foot strip here, right, to withstand the load as well. Because there's two features that is going to withstand the load, right? It's the strength of the concrete and the amount of reinforcement. So the next video, I'm going to do the amount of reinforcement for this 1 foot strip, and then when I get that amount of steel, then I can run it right through this 12 feet length. So if I get 2 steel to go into this slab here, this 1 foot strip, I know that it's going to be 6 times 2, which is 12, because I just take a 1 foot. Every foot is going to be 2. For every foot, it's going to be 2 reinforcing beams with 2 reinforcing steel at the top. So it's going to be 12 overall into the full length of the slab. All right. And remember now, the reinforcement in a cantilever beam or a cantilever balcony, the reinforcement goes at the top, because the deflection is going to be downwards and you want the reinforcement to be at the top to resist against the downward deflection. All right, so that is it for this video. This video is a long one, but I ensure that I try to explain it as best as possible for the benefit of someone who want to learn or want to understand the video in detail. So next week, as I said before, depending on how this video perform, I might do the reinforcement calculation for the cantilever slab. All right, take care, enough respect, and I will catch you in another video. Maximum respect, man. Take care. All right, good.